Hello everyone. Welcome to Chapter 5, Computing Components for CS110 at LaurelRidge. My name is Amit Brambhat, and today we'll just go over this presentation and understand computing components. Today we'll decode parts of computer in everyday language. We'll start from the specs you see in the ads and walk you through the classic von Neumann model, CPU, memory, storage, and I/O. Before we tour memory organization, the fetch execute cycle, storage devices, touchscreens, embedded systems, and parallel computing. By the end, a messy spec sheet should read like a simple map to you. So what are the goals? By the end of this chapter, you'll be able to read a computer ad without blinking, name of parts of a von Neumann machine and what each one does, explain the fetch decode execute cycle, and describe how memory is organized and addressed. If any of that sounds unfamiliar now, don't worry. We'll take it step by step and translate the jargon as we go. Next, you'll be able to name common auxiliary or secondary storage devices, describe three kinds of parallel computer configuration, and spot embedded systems in your everyday life. Think of phones, thermostats, cars, watches, even computers are hiding in plain sight, and you'll be able to identify what they are doing and why. Let's warm up with a typical computer spec. When you read 8-core CPU, 3.2 GHz, 16 GB DDR, 1 TB SSD, here is the human version. The CPU is the cook, gigahertz is how fast it works, RAM is the size of your counter space for active tasks, and the SSD is your pantry where you keep everything long term. Graphics, ports, and display specs tell you what you can see and connect, like monitors, cameras, and storage. Sizes in perspective. Admiral Grace Hooper used hands-on props to explain time at computer speeds, microseconds, nanoseconds, picoseconds. The idea is simple. These tiny time slices are real, and delays of just a few nanoseconds pile up when you do billions of operations. Keep that intuition. Every wire and device introduces a little weight. For time, we speak in powers of 10, micro, nano, pico. For storage, we live in powers of 2, bits, bytes, kilobytes, and so on. Knowing which ruler you're using avoids confusion when comparing capacity or speed. Also, it's useful to look at the prefixes and abbreviations of each of those different powers. Now, with specs, which specs want bigger, faster, or smaller? CPU speed 2.66 gigahertz or higher, faster is better. SD RAM size and speed 4 GB 800 megahertz, bigger and faster are better. Disk transfer rate 300 MB per second, faster is better. Flat screen dot pitch 0.28 millimeter, smaller is better because pixels are tighter and the picture is sharper. Stored program concept. In a von Neumann machine, instructions and data live in the same memory. The CPU fetches an instruction, maybe grabs some data, runs the instruction, then stores the result. Because programs are just data in memory, a computer can change what it's doing by simply loading a new program. No rewiring needed. Memory. Picture memory as lots of tiny mailboxes or cells. Each mailbox has an address. Most computers are byte addressable, so each address points to 8 bits. Example, the cell at address 1111 1110 might contain 10 10 10 10 inside a byte. We often number bits little endian. Least significant bit is bit 0. The table on the right shows addresses and on the right, right column is contents of those addresses. Now, what does 10 10 10 10 mean? On its own, nothing. Meaning comes from interpretation. That same pattern of bits could be an instruction, an unsigned number, a signed number, a character, or part of an image. Hardware and software agree on meaning in context. ALU or arithmetic logic unit. It's the CPU's calculator. It adds and subtracts, and it performs logic like AND, OR, and NOT. It leans on registers, tiny, lightning-fast storage right inside the CPU, so it can reuse values without going back to the main memory. Input or output with answers. Input devices bring information in, example, keyboard, mouse, microphone, scanner, camera. Output devices send results out, examples, monitor or display, printer, speakers, projector. If you can point to it and it communicates with the outside world, it's an I/O. What's control unit? Think of it as an orchestra conductor. The instruction register IR holds the instruction you are executing right now. The program counter PC holds the address of next instruction. Together with ALU, this forms the CPU. The control until keeps every one in time. The ALU does the math and memory supplies the nodes. Flow. The bus components talk over a shared communication system called a bus. Wires or optical lines plus rules of the road. Three kinds of traffic ride the bus: addresses, where to read or write, data, what to move, and control, how and when to move it. Flow of information. Here, the system bus. In most diagrams, the bus connects CPU, main memory, and I/O, often storage, when performance feels slow. It's often because too much is trying to cross the bus at once, like rush hour on a single highway. What's an n-bit processor? Short answer, it can refer to several bits. N might be the size of general purpose registers, the ALU's width, the address size, or the data bus width. Many 64-bit in all these ways, but not always. Peripherals might use a narrower path. Fetch execute cycle. Here's the rhythm. Fetch the next instruction using PC, decode it, figure it out which operation and which operands, get data if needed from the registers or memory, and fourth is execute. Why cycle? Because when you finish, the PC advances and you do it again over and over. In the diagram, the PC points to memory, the instruction moves into the IR, control signals coordinate the ALU and memory, results may be written back, and the PC updates to the next instruction or branch target. That loop is heartbeat of every von Neumann machine. RAM and ROM. RAM, random access memory, lets you read and write any location, but it's volatile. What does volatile mean? It means the contents disappear when power is removed. ROM, read-only memory, is non-volatile. You can read it, not change it during normal use, and it keeps its contents with power off. Perfect for firmware. Secondary storage devices. Why do we need it? Because we want data and programs to persist when power is off, and we need far more capacity than RAM. Examples you can name hard disk drives HDD, solid state drives SSD, optical discs CD, DVD, Blu-ray, magnetic tape, and flash or USB drives. Each trades off cost, speed, and durability. Magnetic tape. Magnetic tape with big drawback. Tape was the first truly mass auxiliary storage. Its advantage is very low cost per gigabyte and long archival life. The major problem? Access is sequential. To reach file X, you may have to win past everything before it, so random access is slow. Magnetic disks. A disk has a spinning platers with concentric tracks, each split into sectors. A movable head selects the track, then reads the right sector as it rotates under the head. This structure gives us decent random access compared to a tape. And you can take some time to observe and absorb the diagram on how a magnetic disk is organized. Magnetic disks with missing def. Seek time is moving the head to the track. Latency is waiting for the sector to rotate under the head. Access time is the total delay to start transfer. Seeks plus latency. Transfer rate is how fast data flows once you are in position. Optical discs, CD family. A laser reads tiny bits and lands along with spiral track. CD-ROM is read-only data. CDDA is digital audio. CD-ROM is write-once read memory. RW or RAM is read-write. RW means read-write. And both read from and written to. These are the definition of optical discs. And then continuing on, DVD is digital versatile disc used for storing audio and video. And Blu-ray is a higher capacity DVD allowing higher resolution. Blu-ray uses a shorter wavelength laser and smaller pits to pack even more, enough for high definition content. Flash drives. Flash memory are non-volatile, can be erased and rewritten, and supports USB mass storage standard. Thumb drives use USB mass storage standard for plug and play. That's why your files show up like a regular disk on almost any computer. Touchscreens. Touchscreen senses where you touch a display. Four common types are resistive, capacitive, infrared, and surface acoustic wave SAW. Each type balances clarity, cost, and whether it supports gloves or multi-touch. Resistive, two thin conductive layers, one with vertical lines, one with horizontal. Pressing the top layer makes contact with the bottom, current flows, and the controller computers. The intersection point works with any stylus or gloves, slightly reduces display clarity. A conductive laminate over glass carries a tiny current from the corners. Your finger steals a bit of charge by comparing charges changes at the corners. The controller triangulates the touch. It's very clear and supports multi-touch, but it needs a conductive touch finger or a capacitive stylus. Infrared touchscreen. A grid of invisible IR beams crosses the screen. Sensors watch the beams. Touching the screen breaks specific beams, revealing the location. No overlay means high image clarity through the frame and alignment matter. SAW or surface acoustic wave is a high frequency sound waves skim through across the glass. A touch absorbs some energy and sensors detect the dip to find the position. Image quality is excellent, but water or dust on the surface can interfere. Embedded systems. Embedded systems with pocket. Embedded systems are dedicated computers inside larger products. Empty your pockets or backpack. What do you have? Likely a smartwatch, earbuds, a key fob, maybe a camera, fitness tracker. All of these are embedded systems doing a small set of tasks reliably and with low power. There are four broad ideas for parallel computing. Bit level parallelism can process more bits at once by widening word size. Instruction level parallelism overlaps steps, pipelining, or runs multiple instructions at once, superscalar. Parallel computing, data level parallelism applies the same operation to many data items simultaneously. Imagine computing all students' GPAs at once. Task level parallelism runs independent tasks in parallel, like thousands of search queries processed at the same time or separate pipeline stages working concurrently. Shared memory parallel processor, communicating through shared memory. Multiple processors or cores share one memory space. It's convenient. Everyone can see the same variables, but you need synchronization so two processors don't clobber each other's data. Think roommates sharing a whiteboard. Great for coordination if you set some rules. Okay, so here we'll conclude the chapter 5 presentation. I hope you enjoyed the presentation and you can bring your questions to the office hour. All right, take care, everyone. Bye.